Okay, I think we can start. So in this last session of Athens NLP, we have the honor to have with us Ferenc Huszár, who is a professor of machine learning at Cambridge University, and he will talk about causal inference. So, Ferenc.
Thank you. Does this mic work? Stop me if it doesn't. And also, I'm going to use this for my whole presentation. So if you can't read this writing, maybe you're too far, so feel free to come closer. Or just stop me if something is not readable. So, yes, my name is Ferenc. I realized that several years of math and physics in school has prepared me perfectly to read the signs in this country, which I'm very, very glad. And I learned to write my name roughly with these Greek symbols. I'm not sure if it actually looks good. So here's my email. Feel free to email me. If I don't respond, email me again. It happens all the time. And this is a website that you will find me at. I'm going to start with a little bit of self-promotion, of course, like all good professors do. I have nothing to do with the left-hand side, but this is kind of a book recommendation. I don't know if any of you have read The Book of Why. A couple hands in the air. So this book came out around, I think, in 2018, and this was about the time when I also realized the importance of causal inference and started paying more attention to it than before. Before this book, The Book of Why, a lot of the books or a lot of the material that has to do with causal inference was not very approachable, a lot of symbols, unfortunately not even Greek symbols in particular, a lot of kind of funky notation that you had to go through and not particularly well-written introductions. This book, The Book of Why, is written by Julia Pearl, who came up with a lot of this causal inference formalism that we rely on, or he's one of the main researchers in causal inference. But it's co-written by Dana McKenzie, who I believe is a journalist or a writer, so like a non-technical writer. And I think the combination of a technical expert with someone who could tame a technical expert and make something accessible worked really brilliantly with this book. So this is actually a book about causal inference, which has so little math that I actually listen to it in audiobook version, so you don't actually have to follow any of the math. So I recommend, if anybody's interested in getting a good introduction to causal inference and why it matters, before you start, diving into the maths, I recommend reading this book. Or even if you've already been diving into the math and you're comfortable with the math, this is a good book to kind of highlight why certain things are the way they are in causal inference, and also how it evolved over time. So there's also interesting historical notes about how different communities approach these questions differently. Another thing, and this is the self-promotion bit, is a blog post that I've written when this book came out, because this is also 2018. And I put this up here because it's a good historical reminder for me that I have ignored causal inference for a very, very long time. So this is roughly 5 years after I got my PhD. And I did my PhD in probabilistic modeling. I worked a lot with Bayesian methods, graphical models. These things also appear in causal inference, and yet I've never really paid that much attention to causal inference until Julia Pearl came up with this book and had an interview which I read, and claimed that all that we do in machine learning is just glorified curve fitting, and kind of attacked the whole machine learning community in that interview. And so I said, okay, I need to actually take this seriously. And I realized the importance of this, and I think this is the first time that I really understood what causal inference is about. So this is still up there. The URL for this, even though it's like one of the most frequently accessed blog posts that I've written, is the worst URL that I have, which is inference.vc/untitled. It just happens that I forgot to give a title to this one before hitting the publish button. Anyhow, so this is just some kind of introductory material that you can go and read if you're interested. Today, what I wanted to talk about, given that this is at the end of an entire, I don't actually know how long, but let's call it a week of lectures on natural language processing, I wanted to give a little bit of an overview on what the main problems are in causal inference and how they relate to what we usually do in, say, machine learning. So I'm going to try and use some machine learning terminology to introduce some of the core concepts in causal inference. And then hopefully, if I don't run out of time doing that, I also brought an example of how this is relevant to language models. And, and then we can have a discussion about what causal inference and the limitations, the mathematical limitations in causal inference, what they mean for agents like ChatGPT and all kinds of things like that. What sort of lessons can we learn from causal inference about the limitations of this methodology? So I promised that there's going to be machine learning terminology that I use to introduce some concepts. And the analogies or the connections that I wanted to make with machine learning is that causal inference is a form of out of distribution prediction. So out of distribution prediction is usually in machine learning when we have some sort of training distribution, say I'm going to call it p-train, that I can sample from or I observe some samples from. And then I have a somewhat related but still different distribution which I will encounter when my model is actually used or when my model is tested, so I'm going to call that p-test. And in a lot of machine learning, we kind of assume helpfully that the training distribution is representative of the test distribution, so these two things are, the distributions are equal. Of course, we might see different random samples. And in out of distribution prediction, we do not assume that equivalence. That's pretty much the only thing. So how is causal inference out of distribution prediction, or in what sense is it out of distribution prediction? Well, usually we assume that when we build our causal model or when we build our probabilistic model of the world, we have access to something that's called the observational data. And by which we mean essentially usually IID sampled, so independent and identically distributed samples from some distribution, which is some kind of data generating process which we get to observe in its natural state. So this is kind of observing the natural state of a system. So one of the examples I'm going to use throughout is that we have gene expressions in some cells, and observational data is making a whole bunch of measurements of different cell expressions. So let's say, or gene expressions, let's say that we have gene A, gene B, and gene C. And we have a whole bunch of cells or a whole bunch of cell cultures, and we measure to what extent gene A, gene B, and gene C are present or expressed in those samples. But we don't do anything to the system. We're not zapping it with current. We're not interacting really with the system. We're just observing how it is naturally. But what we actually care about in causal inference is making prediction in this other world, which is often described as the intervention or interventional distribution. So we want to reason about what happens if instead of naturally observing these genes A, B, and C, I actually intervene and let's say set one of the values, one of the gene expression values to 0. So let's say I'm interested in what happens in these cells if I knock out gene E. So I want to say A equals 0. And the notation that Judy or Pearl invented for this is this do operation. So do A equals Z means that I'm interested in the situation where the value of A, the expression level of gene A, is, say, artificially set to 0. Something knocks out that gene, it's just not, it doesn't work in the cell. And I assume that other than intervening on this variable A, everything else about the cell continues to work in the same way. And that's actually, a very different thing mathematically or very difficult thing mathematically to make sense of what it means for everything else to work exactly the same way as before. But essentially, let's just keep it at the hand wavy level. That's what we are interested in. So quite clearly, the distribution on the left-hand side, which is the observational data, and the situation that we want to make predictions about on the right-hand side, the interventional distribution, these things do not necessarily match up. So, for example, on the right-hand side, we always, the value of A is always set to 0, and we cannot observe anything other than 0, whereas on the left-hand side, we might see some non-zero values for A. So in this sense, we want to build a model based on data from here, the observed data, but then we want to somehow make predictions in this interventional distribution. One thing that I think is important to note is that these interventions may be things that we cannot even do. So maybe hypothetical. I'm not entirely sure how to write hypothetical, where to put the H, but let's just say it's like this. So hypothetical in the sense that in some situations, I can actually carry out this experiment. Maybe with this particular gene, I have a drug or something that knocks out this gene and leaves everything else as before. But there are other situations where this experiment, so to speak, or this intervention it's not even meaningful to think about making that intervention. So I can ask questions about what would happen to the solar system if the black hole in the middle were to suddenly reduce to half its size or something like that. That's not an experiment that we can carry out, but we might still want to reason about those kinds of what-if situations. The other thing to note is that sometimes you can carry out an experiment, but it would be unethical or undesirable to carry out the experiment. So the typical example here is if I want to understand whether smoking causes cancer, I could run an experiment where I randomly assign each of you to either the treatment group and then I force you to smoke, or the control group and I force you not to smoke, and then I observe who develops cancer or not. This would clearly be an unethical and unacceptable type of experiment to carry out in practice. But I still want to be able to reason about this situation without perhaps ever being able to test it experimentally. This is one of the interesting bits about causal inference, is that sometimes you're reasoning about things that we may not ever have an experimental way to really test if our predictions are correct. But in other cases, you can. In some cases, you can actually check your predictions against experimental evidence. Okay, so that's one connection I wanted to make. And the other connection I wanted to make is to transfer learning. Which is another machine learning term that we often use. So in what sense are we talking about transfer learning, and what is transfer learning? So when we say transfer learning in machine learning, and this happens a lot with large language models, for example, what we typically have is we have some sort of task that we really want to solve. And I'm not even going to call this P, I'm going to call this T for task. So I have some task that I want to carry out with my model, and I'm going to call that the downstream task. indicating that this is something that I eventually, after I've done all the training and all the machine learning work, this is the task that I want my model to do in the future. But I may not be able to train a model to carry out this task because perhaps I don't have enough data or I don't have data at all. So instead, I train a model using a so-called pretext task. So these are two tasks in the sense of like machine learning task. So a typical example would be the pretext task could be, in the case of BERT, it would be masked language modeling. So e.g. mask language modeling. This is a task that I have plenty of data for. I can generate a whole lot of snippets of text from the internet and mask out different tokens. So there's plentiful data. It's an easy to train for task, machine learning wise. And perhaps the downstream classification task that I might want to solve is something like, I don't know what would be like a particularly hard task, but let's say somebody say a classification task here. Just sorry? Entity recognition. Okay, entity recognition. You can tell I'm not an NLP person. So let's say that I don't have enough data to train a model straight up for entity recognition, which would be the downstream task, so I instead train for the pretext task, which I have plenty of data for. And when we do machine learning, transfer learning in machine learning, a key question is, how do I, so in the pretext task, I train some sort of model, and I want to take some aspects of this model, and I want to transfer some knowledge transfer some of that knowledge that I learned in the first bit, and perhaps combine it with a little bit of extra fine-tuning or a little bit of extra data from the downstream task, end up with a model that works for this task. And the key question in machine learning when we do this is what exactly can be transferred? What aspect of the model can we assume that carries over from the pretext task to the downstream task? And then another question is, how are we going to do this transfer? How do we take that knowledge that we learned, and what is the method by which we create this transferred model? And transfer learning was ridiculously difficult until deep learning made everything ridiculously easy. So now, when people say transfer learning, almost always, the answer to the what question is layers. The answer to any question pretty much in machine learning over the last 15 years is layers. So typically when we do deep learning, we transfer some layers that we learned from a big neural network to the transferred model. And the how can be different. So it can be either selective transfer of layers, by which we typically mean that you have trained some kind of neural network like this on the pretext task, say a classifier, and usually you assume that the bottom layers are useful for analyzing data because they are close to the input, they are like some representation for your text, but the top can be ignored, or the top of your network, something that's close to the prediction, is too specialized on making the particular prediction in the pretext task, so we are going to throw this out. So the interesting bit is that in deep learning, when we use transfer learning, we use these modular architectures, which are neural networks. The modules are the layers, and the transfer happens by transferring some of these modules and essentially throwing out or replacing with new layers some of the other layers which are too specialized to the task at hand. Something very similar is happening in causal inference. So the main idea is that model has modules, transfer, keep some of these modules, replace or throw out others. Okay, and this is roughly how we reason in causal inference as well. But in causal inference, we don't always have a neural network, and we don't always have this kind of NLP data or computer vision data where this type of transferring the lower layers works very well. We actually have to come up with a more general sort of mathematical description of what the modules are and which ones we are going to transfer from one situation to the other. So again, the pretext task, just to identify what these components are, in causal inference, the pretext task is going to be the observational that's the pretext. We usually assume that you have unlimited data available in this scenario. And then the downstream prediction that you want to make is the actual intervention. You want to answer the what-if question. What happens if I knock out the gene A? So intervention. So if you have the observational data, the most general kind of object that you can learn from it is the joint distribution of variables, say A, B, and C. Let's say that is still the gene expression data. There are 3 genes, A, B, and C, and their expression levels are denoted by A, B, and C. And if I have enough data IID sampled, I can somehow approximate this big joint distribution of this data. In order to identify these modules that I may or may not transfer to the other situation, I can break this distribution down using, I think it's called the Kolmogorov chain rule. I can factorize this distribution in various ways. And for example, I can write it as saying, let's call this P of A times P of B given A times P of C given A and B. I make a lot of mistakes when I write these formulas, so feel free to raise your hand or just shout if I'm doing something silly. So in order to talk about these modules that I may or may not transfer, I broke down my distribution into these conditional distributions, and the Kolmogorov chain rule basically says that I can always do this. There is always this kind of way of writing my distribution in terms of product of conditional distributions. So instead of layers, I'm going to talk about these modules. And if I want to figure out what to transfer, I want this distribution, which is denoted as P of B and C, given do A equals 0. That's the notation for it. So this is the distribution under the assumption that I knocked out the gene A and set its value to 0. So I want to build a predictor for this using some of the components on the left-hand side. So what I can notice is that out of these 3 layers, these are not layers, but modules, only one of them is a distribution over A. Only one of them is responsible for generating the value of A. Everything else, so this P of A is a distribution of A. Everything else is the distribution of other things once I know the value of A. So I can say that, well, I don't want this module P of A to generate the distribution of A anymore, because I'm going to interfere, but I'm happy to keep the other sides of the equation. I'm happy to keep these other factors intact. So I'm going to build this distribution on the right-hand side by taking I'm going to write this with black. So I'm going to keep P of B given A, P of C given A and B, because these are the distributions that are responsible for what happens to B and C. And this one I'm going to throw out, and I'm going to replace it with something else. And the thing that I would replace it with is a delta distribution, in this case, delta of A. And this is notation for, it's basically a probability distribution that puts all its probability mass to A being 0. So if you're working with discrete variables, this is a distribution that has probability 1 when A equals 0 and probability 0 for any other value. So this delta A is here to represent the fact that I now assume that A's value is fixed in this world. And if you notice, I've written this equation here as being the distribution of B and C conditioned on something, so it's not a distribution of A. So in order to get rid of the A, I'm also going to integrate it out. I'm going to write dA. So that's integrating the value of A out, or summing over all possible values of A. This is if we are dealing with discrete values, this is going to be a lot easier. The point here was that now that I identified these different modules, I could decide to get rid of some which are responsible for the variables that I intervene on, replace them with these delta variables that fix their values to a particular thing. And here I gave a mathematical meaning to what it means to assume that otherwise the system behaves like before. And that's where the black parts come from. Okay, so this is a little bit, this is the analogy of taking a neural network and, saying that some of the layers are useful in the other tasks and some of the layers are too specific. That's roughly something that's happening here. So who can tell me what the problem is that I haven't talked about yet? What is the issue with what I've said so far? So, am I done? I can learn the joint distribution of A, B, and C. I can factorize it in this way. I can throw out this component and then calculate this distribution on the right-hand side. And now I know how to make distributions or predictions under intervention. Who can see a problem with this? I can repeat the question, I think, if I can hear it. Okay, yeah, good point. It's not what I thought about, so if anybody has other, keep your hands up. So the answer was, or the suggestion was that it's not possible to integrate this because it's not continuous. Yes, in the case it's not continuous, it would be potentially a sum, but also, and then the sum, because it's a delta distribution, would turn into something very trivial. But there is something deeper there, which is that I may not be able to easily calculate this value. So mathematically, this thing exists, but I may not be able to accurately or even to any arbitrary accuracy estimate its value from data. It just may be too difficult a sum to do. That's not what I thought about, but that can be an issue. Anyone else? Anyone else? Okay. What's your suggestion?
So what you will calculate if you do that, it will be just the conditional probability, right? The P of B, comma C, given A equals 0. But that's not what you really want, right?
Okay. So the suggestion is that this is the same as P of B, C given A. In this particular example, it may be, but in general, this may not necessarily be that. So maybe in this particular toy example it is, but in general, it's not necessarily the same. Not necessarily. So what I mean by not necessarily is that if for intervening on A in this particular thing, yes, it's the same, but if I intervened on B or C, I would get a different answer. So for B and C conditioned on do A equals 0, I actually get, yes, the same thing. Any other ideas? Of what did I gloss over? So I said I have my distribution here, this thing. I can use the Kolmogorov chain rule. I can break it down to factors. And then once I have the factors, I can do this calculation. Any issue? I can tell that it's in this part.
So are the A, B, and C, are these the outcome classes? Or what's the
So the A, B, and C are, let's say in this toy example, they are variables representing the gene expression levels. So let's say they are numbers. Yes?
what happens if you have all of them?
Like not just A, B, and C, but you have a million of them. Yeah, that's also a good question. Then everything becomes a lot more difficult to estimate, I guess. But I think mathematically there is not a huge difference necessarily in there. Yes, someone at the back.
Is it possible that you cannot express in the detail each component because you only see the joint distribution?
Okay. Yes. I promise to repeat the answer. It's possible that we cannot express all of these factors, these three factors here, this one, and this one, because we only see the joint distribution. And I'm going to take that as a correct answer, but say something even more problematic with this. The Kolmogorov chain rule, which allows this decomposition, can be used in arbitrary ordering of variables. So I can also identify a different set of distributions. So this is a slight mathematical abuse that we are used to in machine learning, where the arguments of P denote which distribution I'm talking about. So if I say P of small a, I mean the distribution of the random variable A. And if I say P of B given A, I mean the conditional distribution of the variable B given A. So I can also write P of A, B, and C as, for example, P of C, P of B given C, P of A given B and C. Okay, so now obviously these P's are different P's. That's what I meant. So this is now the marginal distribution of the gene's expression level of C. This is the conditional distribution of B given C, and so on. But I now have broken down my formula or my joint distribution to modules, but now my modules are completely different modules. And so if I would do the transfer in this world, I would now throw out this third component, for example, because that's the component that's responsible for generating the value of A, and I would keep these other components here. And I would arrive at a completely different conclusion. So the problem is that the breaking down of the probability distribution to these little modules, which are responsible for generating each of the variables given some other variables, is mathematically non-unique. I can do it in any particular way that I like. In fact, there is 6 different permutations of the letters A, B, and C, so I can write 6 different ways, and they can all be, that all those breaking up of things would be equally valid. So the problem is, I'm going to draw this favorite diagram of mine that appears in almost everything that I do. So I have a potato. This potato is the set of probability distributions. So this is joint distributions. And then here, let's say over 3 variables, just to make it clear. And then the other potato, which I'm going to draw bigger, is the Markov factorizations. Over 3 variables. So the Markov factorization, which of course is a capital M. So the Markov factorizations are these guys here. So when I break up the distribution in a particular order to a product of conditional distributions. And the problem here is that if I have a distribution here, the mapping between them is a one-to-many mapping. So if I look at if I have a particular joint distribution, there are different Markov factorizations of that joint distribution, which are all equivalent, which all would give rise to the same joint distribution, but they might support different causal conclusions. So it's possible that if I assume that this is the correct thing, and then I make a prediction about what happens in the intervention, I reach a different conclusion than if I assume that this is the correct factorization and then carry out this transfer. So this ambiguity of how the joint distribution is broken down to particular Markov factors is essentially like the big central problem or the big central question in causal inference. So this is a many-to-one mapping, or a one-to-many, sorry. So if I flipped it around, it would be many-to-one. It's a one-to-many mapping. One-to-many mapping. And this means that if you want to actually if you want to predict what happens under interventions, it's not enough to model the joint distribution of the data. You need a full causal model. Which is a Markov factorized joint distribution. Or another way to say what a full causal model is it's a joint distribution plus some information that encodes how I'm supposed to break it down into these factors, which can be described by a causal graph. So for example, if I have A, B, and C, sorry, this is an A, it's not very visible. Then if I have this graph between A, B, and C, what this means is that for every node, the other nodes which have direct arrows pointing to it are called their causal parents. So the parents of B is the set A, because A is the only node that points an arrow towards B, and the parents of C equals B, and the parents of A equals the empty set, because there is no arrows pointing to A. And so if I have a directed acyclic graph, a DAG, that encodes these parent relationships. And then I can do the factorization as follows. I can say P of A, B, C equals the probability of A given its parents. In this case, A doesn't have any parents, so it's just the probability of A. Then the probability of B given its parents. In this case, the parents of B are only A. So that goes there. And then the probability of C given its parents, and now the parents of C is the set that only contains B. So this is the sort of equivalence between a directed acyclic graph, which we call the causal graph or the causal diagram, and a particular way of factorizing this distribution. Okay, so very important takeaway from this is that in order to make these causal inferences, which is to estimate what's going to happen to a system if you intervene, if you artificially change some values, you need not just a joint distribution of that system, but you need somehow this additional extra information, this causal graph. And this can come from different places. Sometimes you can estimate some aspects of this causal graph from experimental data, but in general, this may be something that you have to supply yourself. Yes, there's a question.
And we assume that the causal graph is deterministic, not probabilistic, right? So we know for sure that B depends on A.
Yes, yes. In this case, the causal graph is just a graph that encodes what depends on what else. Yes, that was the question. The question was whether it's probabilistic, or the comment was that it's not a probabilistic. You can probably make some sort of hierarchical model where you also assume that you have insufficient knowledge about those causal relationships. That's probably a slightly different issue. Okay, so the typical example is, for example, if you have two variables, x and y, or a and b, and you don't know anything else about these, you can just observe IID samples from some joint distribution over a and b. It's probably not possible, or mathematically not possible, to tell whether the arrow goes from x to the y direction or the arrow goes from the y to the x direction. Both of those ways are possible ways of writing that distribution. But I think that's sort of where I wanted to end with the general discussion of causal inference. I'm going to draw a line here. Are there any questions about any of these?
Follow up what I just said. So is that the main difference between probabilistic machine learning and this causal inference? The fact that in this case you do have some things that are 100% true, whereas in probabilistic machine learning,
so the question was,
it's always a probability. It's not.
Yeah. So the question was roughly like, what is the relationship between probabilistic machine learning and causal machine learning? Is that you are probably right. I think the intuition comes from the fact that we use probabilistic graphical models all the time, even when the goal is not to do causal inference. And the main difference is that it might be a nice thing to do anyway, even if you never want to answer any causal questions. But if you want to answer causal questions, the only way we know of how to do it is to build a probabilistic graphical model, and that graphical structure has a central role to play. And different graphical structures differ fundamentally in what sort of conclusions you might reach. Maybe that's a way to answer that question. So you can use probabilistic graphical models which have DAGs and everything anyway, but if you want to answer causal queries, then you kind of have to think about them. There was a question from a little bit behind.
If I'm understanding correctly, the information about causal graph is somehow solving the problem of one-to-many mapping. And I was wondering if, like, is there a selection criteria of a causal graph, or having a ground causal graph, or, sorry, gold causal graph, or maybe it's study-based or hypothesis-based? Because, yeah.
Yes, yeah, so that space which deals with how do I figure out what my causal graph is from in some data-driven way is generally called causal discovery. So causal inference is basically, you know, there is not a clear line between when you stop calling something something else, but causal inference is, I assume that I know a causal graph, it's given to me somehow, maybe it's an assumption that I have, maybe it comes from data, or somebody gave it to me, and then how do I use that causal graph to do this transfer? How do I make that prediction? And causal discovery deals with the question, I don't know what my causal graph is, or maybe I'm uncertain about some aspect of my causal graph. How can I, in a data-driven way, say something about it? And that's a whole new, it's a whole different lecture to go into those methods. All right. So I said that I'm gonna bring you an example that is language model inspired or language model related, which is making a causal graph for the game 20 questions. So 20 questions has different names, I think, in different languages and cultures, and I'm pretty sure that everybody kind of knows this game. There is an answerer and a questionnaire. And the answerer thinks of a concept like Komodo dragon, and then the questionnaire can ask a series of questions, up to 20, I guess, which are decidable questions, yes or no questions, like, is it an animal or not? Is it larger than this table or something? And the answerer then answers truthfully given the concept that they have in their minds. And at the end, once the questioner has enough information, they can ask they can guess what the object was. So I'm pretty sure everybody has played this game once and annoyed their parents to oblivion. I'm a parent myself, so I can relate to that. So for example, I can say animal. I'm not going to write down this example. I think everybody gets this. But we can write two different causal graphs. I'm going to be interested in how humans play this game. So what would be my causal model of a human playing this game versus how an LLM, and in particular an autoregressive LLM, so the kind like GPT models, how they play this game, or what would be a causal model for this. Okay, and I'm going to now focus on my causal model of how the answerer answers a question. I don't care about where the questions come from for this discussion. So I assume that I have, so humans, I'm going to start with humans. So if I'm a human and I play this game, I first of all have some latent variable, some hidden variable that I'm not going to reveal to anyone. It's not revealed, like it's in my head. And I'm going to call it the concept. And it's, say, a discrete variable over lots of different things, or lots of possible different things. And then the questioner asks the first question, Q1, is it an animal? And then my answer is going to be A1. So question 1 comes from somewhere. A1 is the variable describing my answer, which is binary, yes or no. And if I play this game well, as it's supposed to be played, then obviously my answer is going to depend on the question, because answers usually depend on questions, except in political debates. And it's also supposedly dependent on the concept that I have in mind. I'm going to give a different answer if I was thinking of an animal versus not an animal. I don't think this is very controversial. And then I have my second question. Again, I don't care about where the questions come from, so I'm not interested in what influences the questionnaires side of the process. I'm just interested in the variables that the answerer controls. So the second question will have an answer. The second answer depends on the second question. This is not a theta, this is a Q. And then also, the second answer also depends on the concept. Yes?
Doesn't the second question also depend on the first answer?
Yes. So, okay. So that's what I meant by I don't care about building a model for how the questioner asks their questions. But yes, in reality, the second question probably depends on what was the first question and what was the answer. Because if I know that it's an animal, I'm going to ask a different type of question. So that's the questioner. So the questionnaire is, responsible for determining that relationship. But from the answerer's perspective is the green arrows that I care about now. What's very important here is that in this model, I have basically assumed that once you know the concept that I'm thinking about, and once I know the current question that I'm being asked, I don't anymore care about what the previous questions and answers were. So for example, this arrow, which I could have here, is missing. So I'm just going to answer each question truthfully. I don't actually need to know what questions have been asked before in order to answer the next question. Okay, and similarly, there is no arrow from Q1 to A2 either. Okay, and then I have, I have this repeated several times. So this is the DAG that I would write for a human, and importantly, it has this hidden variable, which is a random variable that I assume exists, which describes what was the concept you thought about when you started the game. Now, how does the LLM play 20 questions? It can. You can play this game against ChatGPT. But our causal model for how an LLM does it is going to be very, very different. So again, I'm going to have the questions Q2, Q3, and the first answer obviously depends on the first question. In an LLM, there is no concept. We wouldn't model an LLM as saying the LLM made up its mind that it's going to think of a giraffe and then it plays the game. All that an LLM can do is look at the prefix of its prompt and condition on that and generate something new. So I have that random variable missing. Then again, the questionnaire controls, how the second question is going to be asked. That has nothing to do with the LLM. The LLM is next evaluated to answer the second question. It's going to come up with A2. But because it's an LLM, the way it works is that you plug in your entire chat history. That's what the ChatGPT model is conditioned on. So it's going to actually depend on the previous answer and the previous question. So you have arrows pointing from all the previous questions and all the previous answers to every new answer. And so A3, similarly, you have all of these arrows that you can possibly have. Okay? So what I wanted to highlight here is that it's possible with an LLM to mimic exactly the same distribution of data as humans actually produce. So if you ask a bunch of humans to play this game and the questioner is the same, then the LLM is going to be able to learn how to generate answer question sequences which exactly match the distribution of what was seen before. So the distributions match. distribution may match between human and LLM, but the causal model is different. And this has some implications about how the LLM-based agent is going to actually behave. So let's say that I have a situation in which, whatever the agent, whatever the human or the LLM answers in the second question, I'm just going to flip the answer. So I intervene on A2, and I'm going to say that A2 is actually flipped compared to what it should have been, or I always set its value to no. So let's say that the second question was, does it have legs? And the human, because it thought of a Komodo dragon, it would answer yes. But in fact, let's say that it's played online, so that that there's like a text surface, and the chat surface somehow changes the human's response from yes to no. Now, a human, other than sort of maybe being very puzzled and everything, wouldn't then say, "Oh, I just said no to that answer. That must mean that probably I was thinking of a snake." You're not playing this game and saying, "Oh, if I answered it incorrectly, then I'm changing what the concept is." But that's exactly what would happen in the LLM. So if you change an LLM's answer to the second question to no, the LLM from that point onwards is going to be convinced that you're talking about a snake, for example. So the LLM doesn't have its concept in its head, so to speak, at the beginning of the game. It makes up its own mind about what the concept is that it's answering based on, kind of in the same way that the questioner is trying to figure it out. And so, that's just kind of an illustration that an LLM obviously works very, very differently from how human plays this game. And even if these distributions are perfectly matching, in a real world, like if you change the situation, like if you change the questioner or change something about how the questioner asks the questions, that's the out of distribution situation when you might see the difference between the LLM and the human. The human might respond differently to that out of distribution situation than the LLM. And I wanted to close with two paper recommendations. One of them is, of course, going to be self-promotion again, but that's at this point it's expected. So here is an interesting paper. I don't know if any one of you have seen it. Has anyone seen this paper? Okay, cool. That's my student. Okay, so this is very cool. So what happens in this paper, they train a transformer LLM, like a GPT-like model, on humans playing chess. But the ELO score, so the chess playing ability of the humans in the dataset is capped at 1,000. So it doesn't have any very, very good grandmasters in them. You pre-train on this dataset, and then you turn your LLM into a chess playing agent. And what's interesting here is that if you turn your model into an agent from a generative model, it actually works better than any of the humans that it has seen in the dataset. So it achieves something like an ELO score of 1,300, when the best human in that dataset only had an ELO score of 1,000. They call this transcendence. And how this relates to what we've just discussed is that when you use an LLM as an agent, so even in like a chatbot situation, you're essentially putting it in an out-of-distribution context. And in order to predict what's going to happen, you have to, reason about the causal graph. And because the causal graph is different from how a human would solve a problem, you very likely are going to see different behaviors. It may not be worse than a human. In this case, it's actually better than human. And the self-promotion one, which just came out on Archive yesterday, is, where are we? Is another one. It's kind of looking at a very similar type of thing, but in formal languages. So even simpler than the chess example. It's kind of asking the question, if you prompt LLMs in an out-of-distribution setting, how are they going to respond in that situation? So I think both of these papers are interesting read, but obviously the second one I'm a co-author of, so I probably shouldn't be advertising too heavily. So thanks for staying a couple more minutes than intended. And I think this is the end of your summer school experience, except some questions. Thank you.
So we have a small present for you.
Thank you.
Any questions, maybe?
I have many thoughts, but I will focus maybe on the chess example you brought to sort of demonstrate what you showed us here. So this is a case that, okay, you can read it as a generalization ability of an LLM to go beyond of the trained set, go to out of training distributions and so on. And in this particular example that you guys wrote, like it's a game which is very easy to evaluate what you're doing on the out of distribution domain, right? It's an easy, you know, you lose or you win the game, something like this. So it might be more tricky to do this kind of things in cases where you need to consider sort of epistemic uncertainties outside of distribution.
Yes.
So where you cannot really, you know, uncertainties start getting into the game. And here it's an example that probably you don't have any sort of these uncertainties in a way.
Yes.
So yeah, what about in these cases, how you would approach?
So that's a very good point. So I'm a generalist machine learning person, so I tend to forget what the N stands for in NLP, that it's supposed to be natural language. So both of these examples that I've given here, and to some degree also the game of 20 questions, is in a way a formal language. Like you can list all the different possible questions, all the different possible answers, and you can analyze exactly what you would expect. Or you kind of they are nice to analyze. When we started asking these questions, we started from the very bottom, which is, it's kind of hopeless to say much about natural language, so let's start with something that is the most formal thing we can do, which is formal languages, like Chomsky hierarchy type of formal languages defined by rules. That's what this rule extrapolation work is. And chess, I would say, is much closer to something that becomes quite interesting. But obviously, as this research is going to go on, hopefully we are going to investigate more and more examples which take us closer and closer to natural language. So, for example, you can look at programming languages and ask the questions, if you train on C++ and Python, and now you prompt the language model on some like new version of Python it hasn't seen, can we say something about what sort of behavior do we expect to see in that situation? So that starts to become a little bit, it's not natural language because it's programming language, it's still a formal language, but we can kind of push it eventually, hopefully in a couple of years, closer to saying something meaningful about more realistic looking data sets. But sure, natural language doesn't really lend itself to formalisms. This is why we use neural networks and not logic-based or other kind of linguistics-based tools for a natural language these days.
Okay, thank you for the great talk. I have a couple of thoughts. Regarding this paper, the transcendence I don't know if that's a generalization ability or just interpolation from multiple. So if you have multiple experts with different strengths, the model can learn to leverage those. It's kind of like an ensemble, which works better than each individual. If you could train the model only one expert, could it outperform that particular one expert? That's just a side note. My main question is, I think causal inference could solve some of the hallucination problems of LLMs, because the problem is that everything is probabilistic in LLMs. Every answer is probable, even with small probability, but sometimes that small probability just appears. So are you aware of efforts of combining causal reasoning with LLMs to solve the hallucination problem?
Yeah, I think there were sort of two comments or questions there. So on the transcendence bit, the details of this paper are very interesting, and you will find some answer very close to what you were saying, except that when you deal with this like reinforcement learning type of agents, the sort of ensembling you want is more like majority voting as opposed to averaging of probabilities. That tends to, that provably doesn't perform better. But if you can get closer to modeling something that would be like the majority voting of a bunch of mediocre chess players, that would be a better chess player, just because assuming that they make errors on different kind of positions. So that's and this is an interesting paper that connects that to temperature scaling in LLM. So it actually has a little bit of a theoretical explanation along those lines that you're suggesting. On the other thing about hallucination, I'm not even sure if we want to fix hallucination, in the sense that some hallucination is positive hallucination, in the sense that it's like an example of really good out-of-the-box thinking, and it's a really good kind of the type of systematic generalization that we would want very strong general-purpose intelligence systems to display. But sometimes that hallucination falls short of expectations. So I would not venture into discussing this, because I'm not entirely certain how to disentangle these things. I'm not sure that I want to get rid of hallucinations, because I don't know how to do that without getting rid of the good kinds of hallucinations that are then perhaps useful, if you see what I mean.
So we know that some things are true, right? Like 1 + 1, it's always 2. An LLM sometimes can say it's 3 because it's seen some example somewhere of somebody trolling the internet. Can we, this type of hallucinations I'm talking about, that we know based on reality that...
Yeah, I mean this type of thing is, I would say that some sort of, I'm not sure precisely how causal inference would help, but some like neurosymbolic system where you have, for some things, you actually have some kind of knowledge base. Mm-hmm. And if you could make sure that the LLM's answers are somehow, whenever it relates to this knowledge base, are consistent with the contents of that knowledge base, like arithmetics, would be obviously, I think, very valuable, and that's what people do. I don't think this is necessarily a causal inference question, in as much as, I'm not sure.
Well, I mean, you can generalize. Causal inference applies, it's more general than the same. The apple will fall under the tree, right? So that's just caused by gravity. So that's a causal inference result. So can we, I don't know how can it be encoded if it's in...
Yeah, I think this is something...
symbolic reasoning.
Mm-hmm. Yeah. I think this goes, so that's something that I wanted to comment on, but there wasn't a lot of time, which is, there's different kind of causal inference going on. The kind of causal inference I talked about is helpful when you're reasoning about, how certain tokens in the future are influenced by tokens in the past in a language model, and what happens if you kind of change some of those tokens. There is another way in which an LLM is able to causally reason by generating human text that describes causal reasoning. So when an LLM says, this happened because that other thing happens, that's a completely different kind of world. That's like somehow in the natural language, it's able to like draw those conclusions and describe causal situations. And I don't think that the limitations of causal inference apply there. So it can, it can solve math problems out of the box potentially. Like any autoregressive model can potentially output the right answer to a question, and that right answer might involve what we would describe as causal reasoning. But it's not the same sort of probabilistic causal inference that I described when you have these random variables of the tokens. So I think these two worlds are slightly different, and that's some place where I disagree with Judea Pearl or disagreed with Judea Pearl before publicly. And yeah, I think there is some confusion, I think, over what that means. And I think that so Judea Pearl's position would be, you cannot solve this, you cannot make LLM solve causal inference without leveraging his causal inference framework, essentially, or leveraging this general causal inference framework. I don't think that's the case. I think that it is possible for an LLM, however trained, to be able to output text which encodes correct causal conclusions. That's a different statement from the causal statements that we're making with Judea Pearl. I think I'm just confusing everyone now, so let's see if there is any other question. I'm happy to. That's the point when I say let's take that conversation offline, because I think that would be the wise choice. There is another question or comment at the back.
Hi, somewhat related to what you were saying now. If we add a memory module, an external persistent memory to an LLM, would that be more appropriate for causal to create a causal graph in this way? Because essentially what you showed in the 20 questions example is that for each token, the LLM has a chance to, or it has to clear its, to rethink about the state that it is in, essentially.
Yes. So, yeah, it cannot first think of something and then, given that thought, generate some other things. So there are different ways of solving this problem. There are, I forgot what they are thought, but there are these latent tokens. So you can give like an inner voice to the transformer, which means that some of the tokens are visible to the end user, but there are special tokens which say, I'm just going to go away and think about this, a little bit like the O1 model of OpenAI is doing. I'm just going to do my own chain of thought thinking, and then I'm going to finish that and then respond to the user. So these kind of inner voice tokens could be a potential solution for this, because O1 could go, let me think of a concept, and then it has it in its own little memory, whatever, prompt, which is hidden from the user, but is there. So that's one potential solution. I think the key limitation here is that other than the randomness involved in generating the tokens, the transformer architecture doesn't contain random numbers. There is no random computation that's going on in there. So if you ask it to flip a coin and tell you what it's going to do, the point, you're going to get a random answer. So you can try it many times. You're going to get different answers. But that whole randomness comes from that final step of the random number generator deciding which token to generate from the predictive distribution. So you're really, in that case, not probing the LLM's ability to generate random numbers. You're just testing that random number generator at the very end of the generation pipeline, that kind of last bit, if that makes sense. So yeah, I think the point here is that the only reason why the inner representation of ChatGPT can evolve in a random way during a conversation is because of the randomness of the tokens that it generated. And then those random tokens are then fed back into itself, and that's how it can have random representations inside. So that's I think the fundamental problem to be solved there.
So that's a problem because it's not going to be probabilistic. It's going to be more deterministic. I didn't understand why this is.
So, I mean, it is going to be probabilistic in the sense that if you know, what the language model thinks, you know, what its intention is, if you kind of put a label to that somehow and say that this is what the language model is going to do in the next part of the generation, after it generated 10,000 tokens, because those 10,000 tokens are already generated and they were random, what the inner state of the LLM is after those 10,000 tokens is going to be random. But there is no hidden randomness. All the randomness is the randomness that's already present in the generations. So there is nothing that happens inside an LLM which is random, which is not obvious from looking at the tokens that it's already generated. I think that's what I'm saying. And this has a lot of implications to AI safety, like how can an LLM decide that it's going to deceive you when it cannot possibly have this kind of intention of deception. It just infers the fact that, oh, I've done this before, maybe I did this because I wanted to deceive the user, so I'm going to continue deceiving the user. If you want to kind of, this is why anthropomorphizing these LLMs has like very, very big limits, because causally these LLMs work very, very differently. This is why they're also susceptible to adversarial attacks, because you can just change the inputs to the LLM in an out of distribution way and completely influence what it's going to be doing.
One final maybe question?
So with this last statement, basically you're saying that exploiting with in a serial way is kind of like trying to generate the LLM.
Yeah, so you can... So for example, if you train an LLM on 20 questions, like humans playing 20 questions, and then if you want to jailbreak the LLM so it always thinks of something rude, for example, the rudest thing that's in the database or something, you always want it to think of Komodo dragons, let's just say it's a rude thing. You can potentially do out of distribution things like, what if I ask the same question 100 times? The LLM will not have seen that happening in the real distribution, so you can potentially push the LLM completely in a regime where it doesn't really know what to do anymore. And you may be able to, like if you ask it 1,000,000 times, does it have legs? Eventually it's going to say yes, even if it said no 300 times. And we have seen these kinds of attacks, adversarial attacks on, I think even like ChatGPT models or something, where if you just ask something 1,000,000 times, eventually it's going to tell you the answer. It's going to do something that it's not supposed to. And that's because you're taking the prompt so much out of the distribution that it is supposed to be comfortable with, so to speak, that you can influence its behavior. Whereas if you ask the same question 1,000,000 times to a human, which is what my son does all the time with me, then, I'm still not going to change my opinion about, I still think of Komodo dragons. I might say, let's stop this game, but I'm not going to, he cannot adversarially manipulate me. At least I would like to believe that's not possible.
Okay, so let's thanks again.
So, I guess this is the end of the summer school. All right.
Thanks all. Thank you all for being here. It was a great experience for all of us. Primarily you, the universities, your universities, Demokritos for hosting this event, the sponsors, the organizing committee, and of course the speakers we had. Including Ferenc. So, and the volunteers, I told the volunteers, of course. Last but not least, the volunteers. Yeah.